physicists in the world, I have to say, Sabine. And Sabine wrote a book, which I have it here in English, Lost in Math. I just told Sabine that I am the first person who actually received the signature from Sabine and on the book, and I'm very, very proud of that. And this book of Sabine, Lost in Math, was translated by Humanitas recently, and it's called Rătăciți, prin formule. And I'm here with Sabine to talk about her book and her work and her ideas. And I have to say, Sabine, that I did a little bit of homework. That means I asked my Romanian fellows, what questions would they like to ask you? So I have here 2 pages of questions. So I'm not so sure that we are able to do all of them. But first of all, welcome, Sabine.
Nice to meet you again.
Yes, welcome. For the Romanian friends, I know Sabine, and many people in Romania actually know you from 2 things. From your back reaction blog, which is very popular. So people are here, back reaction blogspot, the blog of Sabine, and also from the YouTube channel, because you launched a YouTube channel more or less about 1 year ago, and you already have more than 100,000 subscribers. And there are people who follow you. And I have to admit that there are a 3rd category of my friends. They are really physicists who know you from the physics community. People like, for example, Cristian. Of course, they read the scientific papers. I know that you are a research fellow at the Frankfurt Institute for Advanced Studies. So my first question is also for curiosity. What do you research at the moment? Can you tell us in like few words, what do you research at the moment? What is the subject?
Well, since you ask at the moment, I'm actually technically on vacation. So you see how my vacation is going.
I go to the next question then.
Yeah. No, so I work on modified gravity. Or superfluid dark matter, whatever, which way you want to look at it. So for me, that's the exciting part, is that it's somewhat unclear whether it's dark matter or superfluid, whether it's superfluid dark matter or modified gravity. So I think that's an interesting approach, which has a potential to solve a lot of problems with explaining data out there in astrophysics. So that's basically my day job, you could say. I have a side interest in the foundations of quantum mechanics, where what I've been working on like in the past weeks with my postdoc, and we're just about to wrap up a paper that is supposed to go in the archive next week. So, you know, fingers crossed that there will no problems appear on the weekend.
Hopefully not. We know how it is with researchers. Because you asked that you are actually working on the fundamental problems of quantum mechanics. I'm going to cite something from your book, cosmologists Joe Silk and George Ellis, who said, theoretical physics risks becoming a no man's land between mathematics, physics, and philosophy that does not truly meet the requirements of any. I found this quote very nice, again, from your book, Romanian Readers, Rătăciți, prin formule, editora Humanitas. And so I have a question from one of my readers who wants to ask you, what do you think are the major foundational problems of quantum mechanics? So the major foundational problems of quantum mechanics, if there are any.
Yeah, well, so if you're asking about quantum mechanics specifically, not quantum field theory, which is a bigger problem.
No. More like the principle of quantum mechanics.
I think there's only the measurement problem, and all the other problems that people like to talk about, the supposed problem with non-locality, just to name one, I think they come from not having solved the measurement problem. I know that a lot of people would disagree with that, but I think there's really only this one issue.
I see. So by the measurement problem, you include, let's say, the collapse of the wave function during the measurement and all the macroscopic...
Yeah, the absence of having a physical process for that collapse. You know, there's only the measurement update, the postulate that after you've measured it, it's in a different state, but how does it get there?
Yeah. talking about the problems, actually your book is called Lost in Math, How Beauty Leads Physics Astray. And Vladimir wants to ask you a question which is related to the book. Why the foundation of physics have not progressed for the last 40 years? 40 years, something you remember also, you write also in the book, that in the last decennia, really things didn't pop out from the fundamental theoretical physics.
Yes, maybe let me back up a little and explain where the 40-year number comes from.
Yes,
so
good idea.
in the foundations of physics, we currently use two different theories. On the one hand, we have Einstein's theory of general relativity, which we use to describe space and time and the curvature of space and time and that effect we call gravity. And then we have the quantum field theories that underlie the standard model of particle physics. And in the standard model of particle physics, we have 25 particles and their interactions. So these interactions are usually labeled by three different forces. That's the electromagnetic force and the strong and the weak nuclear force. And so general relativity is more than 100 years old, and the standard model of particle physics was, the theoretical machinery was completed in the 1970s. And ever since then, the mathematical structure of the theories that we used has not changed. And so that's not 40 years, but it's 50 years. I'm, giving physicists a little bit of a bonus there, because, you expect there to be some, period in which people are trying to come up with new ideas. And that indeed happened in the 1970s, 1980s. This is when ideas were born like string theory and supersymmetry, grand unification, and so on. And these ideas were tested to the extent that they were testable, and they were ruled out. Now the problem is that what has happened after this is not that physicists gave up on these ideas that didn't work. Instead, they insisted on using similar ideas over and over and over again, and it just didn't work. So they clearly didn't get the message. They're still looking for supersymmetry. And they still haven't found it, and they never gave up on grand unification, even though it clearly didn't work, because you can always make your theories more complicated. And so this is where this number with the 40 years comes from. And now to the question, like, why haven't physicists made progress? Whether that's in the subtitle of the book, basically. They've been led astray by beauty. That's my argument. And I explain very, very carefully in the book exactly what I mean by beauty. So it's not the everyday man beauty, beautiful sunset or beautiful flower, that kind of thing, but it's a very rigid type of mathematical beauty that physicists in these disciplines just assume the theory must have. And I'm saying, you're putting the carriage before the horse. You shouldn't start with postulating that nature has to obey a very certain, very specific type of beauty, but instead you should be more open-minded about what nature may be like, and then you will find beauty.
Yeah, I agree. I was just thinking that maybe we have to give up being physicists, working with mathematics and thinking like in social sciences or economics, where if you look in economics, there is not beauty. But anyway, I come back to the supersymmetry, which you mentioned, and I'm going to cite you again from your book, where you say, after 20 years in theoretical physics, most people I know make a career by studying things nobody has seen. I would say nobody has measured or nobody has observed. And I was thinking, probably you're referring to supersymmetry. And then I have here some questions from the readers, because the general public has the perception that you oppose the construction of a bigger particle accelerator than a Large Hadron Collider. And Daniel and Klaus Konsmin wants to ask you, why we do not need larger particle acceleration? And Marius continues, don't you like to see new particles coming to life? It's like people in Romania perceive you that you say no to big acceleration in Europe. No. Would you clarify that? Like Cosmin asked, why we do not need larger particle accelerator? Everybody wants to see new particles to life.
Yeah, well, that's exactly what I'm saying. We do not need a larger particle collider. And the reason is that there's absolutely no reason why this collider should see any new particles. The standard model is complete. There are no particles missing, except possibly there's something weird with the neutrinos. We know that. So there has to be something more, but we're not going to find an answer to that until we reach energies that are like, 13 orders of magnitude above what even the next bigger collider could do. So it's far, far, far out of reach. And then even beyond that, there's quantum gravity, which is also something you will want to test, but the collider is not going to do it. And so the issue with building a next larger collider is it's extremely costly. Like even if you compare it to the next most expensive experiment you can think of in the foundations of physics would be basically putting telescopes on satellites. Very, very expensive, goes in the ballpark of $10 billion, something like that. That's the small price tag compared to a bigger collider. And yet there is no good reason to do it. There's nothing to find there. We don't even have a reason to think that there's anything. And particle physicists just keep on repeating the same story about dark matter. That's one of these things. Supersymmetry also, like supersymmetry that has not been found over and over and over again. Dark matter is a similar story. No one has any idea that dark matter is indeed made of a particle. We have no evidence that it is actually made of a particle. And if it is a particle, there's no reason why this particle should be in the mass range that the next larger collider would be able to test. And so the issue that I have, if we take this huge amount of money, and we're talking about something like 20 billion construction costs, and then if you count the operation costs, that's another 20 billion. So we're talking about something like 40 billion euro. If we use the money for that, the money will not be there for something else. It doesn't matter how you look at it. That's just basic economics. And I think the world has bigger problems right now. And even if you look only at the foundations of physics, there are just better things that we can do with the money. And it's not only about the money, it's also that if you invest this amount of money into a very specific area, that's going to attract people. So there will be a penalty for other areas in the foundations of physics where they will be lacking smart people, basically. And I'm afraid if we build that thing, then 40 years from now, we'll be in exactly the same situation. We will still not have any answers to the questions that have already been unanswered for 40 years.
Yes, I saw that you mentioned quantum gravity, and I have to admit that I read with very much interest some of your articles on testing quantum gravity, because you are the first person actually who told me, basically, look, Cristian, in your lifetime, somebody may test some aspects of quantum mechanics. And I really found it very nice. So some of the information which you actually provide, I also give it further in the Romanian language for the Romanian readers. But I have to say for the Romanian people who are now following us, you are also editor of a book which is called Experimental Search for Quantum Gravity, which you published at Springer. And I have a question about that, about quantum gravity from Daniel. He asks you the following: when will we test for the first time quantum gravity, and how? Will we measure the graviton? Will we measure the gravitational attraction of an object in quantum superposition? So in other words, which aspect of quantum gravity will we test first?
Yes, before I answer that question, let me say something about the book. I want to warn you, I would recommend you don't buy the book. I'll tell you how this, it's extremely expensive, and in all honesty, I don't think it's worth the money. It's stereotypically, academically, the kind of book that was printed to be bought by libraries. And it's a collection of proceedings from a summer school that I organized. So that's what it is. You know, I don't want to say.
The point I wanted to make is that you are really a specialist in this field. You know, we are talking
yes,
specialists.
yes. Okay, so great. I've edited a book. Yay! And I don't want to say the book is uninteresting. I'm just saying that for the content, it's a little bit overpriced. You know, the way that these things go. Yes, how are we going to test quantum gravity?
Aspects?
Yes, so it is, I find it extremely implausible that we're going to measure a graviton within the next 1,000 years or something like that. That's indeed the signature that for a very, very long time people have focused on, and therefore they've concluded we're not going to make it because that's what you need these ridiculously high energies for if you actually want to produce a graviton with the probability so high that you can measure it.
If I just add what you wrote in the book is that you have to have a detector of a size of Jupiter very close to a black hole fusion in order to measure the graviton. Is one of the examples you give in the book. So in other words, it's
yes.
very, very difficult to measure directly.
Yeah, if you want to measure a graviton that has been produced by some astrophysical source, you need such a huge detector. Alternatively, you can build a very large particle collider and, you know, bump your protons together at ridiculously high energies. And if the energy is high enough, you get a substantial probability of creating gravitons, and you can measure that because, you know, they have spin too. So it's, and you know, they carry away energy. So you could find out, but it's not going to happen in my lifetime, and I don't think in the foreseeable future. So clearly measuring gravitons is not the thing you want to go for. Now, gravitons are not the only consequence of quantizing gravity. Indeed, there are some approaches to quantum gravity which predict that there are no gravitons. This idea known as emergent gravity, which basically has it that gravity is something like an effective force, or you would say an effective limit. Gravity is more something like hydrodynamics. You know, it's a bulk description of some underlying microscopic structure, and you wouldn't expect gravitons in that approach. So there are instead a few other areas where you can look that I think are more promising. Let me just name the ones that make the most sense to me. One you already named, it's trying to bring very massive, you know, for particle physicists, massive objects into quantum superposition. Yeah, we were talking about something like micrograms, milligrams, micrograms, so in that range. So for the normal person, that's not exactly massive, but if you compare it to the mass of an electron, that's pretty damn massive. And so the interesting thing is that in that area, there's a lot of technological progress. And, you know, people are constantly pushing the frontiers, and there's no good reason why it should suddenly stop. Like there's no, you know, wall foreseeable that could come up. So I think they will just slowly make progress, and at some point get there. And the thing is, if you succeed in bringing particles into quantum superpositions, I'm talking, you know, just to get a picture in your head, I'm talking about superpositions of locations, actually. That's the easiest way to think of it. You can make it more complicated, but that's the simplest thing to have in your mind. You could just measure the gravitational field if these things are heavy enough. And then you would know what the quantum properties are of the gravitational field. There are related ideas that people have pursued. For example, there's this idea that you could try to demonstrate that the gravitational interaction between two objects can create entanglement. And the idea there is that you can mathematically show if this interaction can entangle two sources, then it must have had quantum properties itself. In principle, that's all fine and correct. I can't really see how you would rule out that it came about in some other way. It seems to me very, very challenging. So that's these would actually be tabletop experiments, and they would not cost 40 billion euro.
Okay.
So it's definitely something to push. Another area that is promising in principle is that you could look for imprints in the cosmic microwave background. So the idea is that quantum gravitational effects would have been much, much stronger in the early universe. And this would have affected the spectrum of the density perturbations in the plasma, which eventually goes on to create the cosmic microwave background. The challenge there is that you have to find a signature that could not have been created by classical random fluctuation. So you need to find something that has quantum effects written all over it. And this is possible in principle, but right now the situation is that either it's something that you can measure, but then it doesn't have, it's not necessarily a quantum effect, or they know that you can only get it with a quantum effect, but then they cannot currently measure it. Yeah. So, but again, I mean, this is an area where people are making a lot of progress, and maybe one day we'll get there.
I see. So you went back to the beginning of the universe. You said something about inflation theory. So I have a question actually about it. You mentioned in your book, you say cosmologists Anna Ijas, Avi Loeb, and others complain that due to the large number of models, inflationary cosmology, as we could currently understand it, cannot be evaluated using the scientific method. So there's something I tell you something these things because the people who are listening us, the Romanian readers, they know also what are you talking in the book. So for the Romanian readers, you are going to find in the book, let's say, an overview of the fundamental problems of physics today. And inflation theory is one of these well-discussed problems in physics today. So that's why this is, Sabine, for Romanian readers to buy the book, because they are going to find out what people talk about physics today. But about this inflation, I have this question from somebody who said, do you think inflation can solve the problem of cosmology? What is good and what is bad in inflation theory? What do you think is good actually?
Okay, so this question, you know, it would take a 3-hour lecture to answer, but I'll try to shorten it up a little bit. So first, maybe let me clarify that inflation is not a problem. Inflation is a particular type of theory for the early universe, and it's debatable that it even solves the problem. That's what my book's going on about. Like there are certain features, you could say, of the current standard cosmological model, which is called lambda CDM, or sometimes it's called the concordance model, same thing. So that's basically general relativity with a cosmological constant and dark matter. And you can run this backwards in time, and it will tell you how the universe looked like. But then what happens is, if you go back in time, you're squeezing together the matter, and it gets hotter and it gets denser. And at some point, we reach an energy that's so high that we have not actually been able to test it on Earth. So that's, roughly speaking, its energy is higher than what the LHC has tested. And at that point, we really don't actually know what's going to happen. You can, of course, just, you know, continue to run these equations backwards, but, you know, that's just speculation. And now what's with inflation? Inflation was, ironically, was solved it was invented by Guth to solve what's called the monopole problem. The supposed problem there being, why haven't we seen any monopoles? To which the answer quite possibly is, they just don't exist. You know, it's somewhat weird. Why do you think it's a problem that we haven't seen something that we have no evidence for? So, but then it was later recognized that the same mechanism of this exponential expansion in the early universe would solve some issues that have given headaches to other people. That's the supposed flatness problem and the supposed horizon problem. And the reason I formulated this way is that I don't think these are problems. And if you talk to cosmologists who have thought about it carefully, they will agree that these aren't problems. Okay, so I've had this conversation many times. And now here is where it gets complicated. There are other issues with lambda CDM that I actually think do need something like inflation to solve. So I'm not actually opposed to inflation. I just think that the reasons that people normally bring forward are not good reasons.
I see.
So,
so I know if I understand you correctly, for you,
typically scientific answer. You know, it's complicated, and then in the end, no one knows what.
No, but I think you have here a point, because for you, inflation is not like a theory, you know, a general theory of relativity, but it's rather a set of models, and you can borrow the models for doing something else.
Yeah, you can also do something else. Actually, to come back maybe to this quote about the complaints by what's her name, Ilias or something.
Anna Ilias, Avi Loeb, and
yes.
Paul Steinhardt.
Yeah, God knows how these names are all pronounced, but yeah. So I think one of their complaints is that inflation was supposed to solve some kind of fine-tuning problem, and their argument is it doesn't actually solve the problem. Now, I think that the problem was never a problem in the first place, so I'm not particularly bothered by that. But what they have a point with, I think, is that these models, you know, if you look at inflationary models as a collection, it's entirely unpredictable, because whatever data is thrown at you, there will be some model that can accommodate it. And people who claim otherwise are just, you know, I don't want to say lying, but yeah, they're casting a too positive light on the situation, let me put it like this. And the issue is simply, and cosmologists are always offended when I say this, but I'll say it nevertheless, there is not a lot of data in cosmology. You know, it looks like it, you know, if you look at the CMB, you know, power spectrum, what have you, but compare this to particle physics, where, you know, you bang your protons into each other and then you have terabytes of data, basically. There's just, you don't have this in cosmology, and you end up with a model like lambda CDM or in inflation and so on, where you have like a dozen parameters or something like that. And now if you, you know, you create your inflationary model, the only thing you do really is that you take the parameters that you have extracted from observation and you somehow convert them into the parameters in the model. But then you're not predicting anything. The only thing you've done is you've parameterized your data. So it's completely useless.
Okay, but you know, people still believe and dream of a unified theory, of a theory which has everything in it. And I'm going to quote something which you write in the book, and I really liked it very much. You actually have it twice in the book, and it's good so that it sticks in the mind. Math keeps us honest. It prevents us from lying to ourselves and to each other. You can be wrong with math, but you can't lie. And here comes the question, which is actually from our friend Cristi Stoica, a physicist like us, talking about this unified theory. Do you think that a unified theory of physics is possible? If no, why? If yes, do you think that one of the known models has better chances? So in other words, do you believe in a unified theory like most physicists believe? And if so, in which direction? Which model would give you more chances?
Well, you know, I would say I'm a scientist. I don't know how to answer to questions of belief. You know,
but belief for a scientist is basically on mind, based on what you read. It's not like I believe in God. No, it's something I believe because I read some articles and Sabine told me when I discussed with her last time.
Well, I do think it's a rather religious question because maybe I'll just tell you how I look at the situation. You know, we're having these fundamental theories that I explained in the beginning, the standard model quantum field theory and general relativity, and these theories have problems. The problems clearly need a solution, and that's the way forward. Now you're asking a question about what the solution may look like. Yeah. You know, will it be some kind of unified picture or not? And the answer is, I don't know. I have no idea. I also have, you know, no strong preference one way or the other, because all I really want are answers to these questions. And I've said this many times before, but I'll say it again. I really think that the key to these problems is the measurement problem in quantum mechanics, because I mean, you can ask, why haven't we been able to quantize gravity? And quite possibly the answer to this question is that we don't properly understand how quantization works. And to really understand it, you need to understand how quantum mechanics works, which brings you back to the measurement problem. Right. This is basically why I'm working on it, because I kind of think that if we could manage to make progress there, then this would lead us forward. But again, you know, will this mean that we find a unified description of everything just by solving this problem? I don't know. You know, it may very well be that the only thing that happens is that this just brings up more new problems, right? Because that's the way that it has historically been.
Yeah, we don't really encourage young people now to do physics. More problems are coming, more problems. But because you said that, yeah, because maybe, you know, we are not at the level to understand it. I have a question here from Theodor Nunn, which goes into that direction. Having seen that modern physics did not have any breakthrough in the last decennia, how do you imagine that in the future will be the impact of the artificial intelligence on the research in the fundamental physics? It's like, if people cannot solve the problem, maybe the AI will be able to solve it. What do you think about it?
Yeah, that's a very interesting question. And of course, a question that I guess a lot of people have asked themselves in the past decade or so. So of course, artificial intelligence is not new, but what is new now is that it's become very easy to use, you know, on a level where you can run it on your laptop, basically, what previously you could only do if you had some kind of access to a supercomputer, that kind of thing. So it's become a go-to tool for a lot of disciplines, and including the foundations of physics. And so I think what this will do is, well, maybe let me say one thing ahead. Artificial intelligence is really only useful if you have a lot of data. That's what it's really good at. You need to train it, and then you can use it to recover some patterns. So if you're working on a theory like quantum gravity where there is no data, it's not very useful.
Yeah, very good observation.
There are other areas like dark matter, for example, where there is data. I don't want to say a lot of data, because as I already emphasized, astrophysicists and cosmologists tend to think of it as if it was a lot of data. But if you compare it to other typical sizes of data batches that people are using, it's not a lot of data. But in any case, you know, there's more data is coming in, and AIs are getting better. And so I think that's an area, and of course people are already doing this, you know, where an artificial intelligence might be able to actually you know, unlock some progress because it's less biased. You know, it's an artificial intelligence would not be looking for a theory of a particular type. It would just be looking to recognize particular patterns that we may actually have missed because we're trying to start from a particular assumption of what we are even looking for. So that's an example. And of course, people are also using AI in particle physics to more generally look for new things. It's a little bit more complicated there because they I mean, there's of course also a lot of AI already involved in the data analyses. So it's, you know, sometimes it's not really clear where the data analysis stops and the theorizing begins. And there are other areas like what I think what will happen in the long run, you know, if you allow me to speculate, maybe some
Yes.
100 years into the future or something. I think basically what we'll do is that what we currently think of as doing theory development will move to a meta level where we instead write a code that will develop what we previously thought of as theories. So we will have theories about how the neural network looks that discovers a theory about nature.
Yeah, yeah. I have still some question of physics and some other question from the fields, and I have to decide. I will put just the last question of physics, and then we move to the last part because we have about quarter of an hour left. So kind of the last question, but I will start with a quote from your book. Observational guidance is necessary in physics. Physics isn't math, it's choosing the right math. Really, really very nice. Physics isn't math, it's choosing the right math. So I have a question here which says the following from somebody, says, in what kind of experiment would you support investment to maximize the chances of discovering new physics? So in other words, how would you choose where would you think is the right thing? In what kind of experiments would you invest money if you would be billionaire, Sabine, like Elon Musk? You know?
Yeah. So I get asked this question a lot, and I always have to start with my little prologue, which says, if someone gave me a lot of money, I would not make this decision myself. You know, I would ask other people, and I would, you know, try to understand what they're telling me. It's not that I believe I figured it all out and I'm a genius or something. Now, if you more specifically ask, like basically, what's my current research, you know, what's the experiment that I would want to do? We already talked about this partly, you know, there's quantum gravity, there are these experiments with the massive superpositions with the, they call it an entanglement witness. That kind of stuff. I think that's really, really promising. And there's certainly more that could be done. And money always helps. So that's the one thing. The other thing is that when it comes to the measurement problem, there are some avenues that have just not been pursued. I think there are too many people in the foundations of quantum mechanics who have very narrowly focused on these bell-type tests. You know, there are gazillions of them, and they all do the same test. Drives me nuts, because I mean, how often do you want to test the same damn thing? And there are other tests that could be done that I think would be much more promising, but that are not being done. So this is an example where I would put my money into.
Okay, I too. So coming back to outside physics, I read in the Scientific American, John Horgan, which is a writer who gave an interview at one point, and he said, I have reasons to resent Sabine Hossenfelder. She's a free will denier. And I have a question from Liviu Coconu, who is following you on Facebook and all the other, by the way, for the Romanian readers, don't forget, Back Reaction, Blogspot, and YouTube channel of Sabine. And Liviu asks the following. How do you explain writing a book to prevent non-scientific physics while being a super determinist and free will skeptic? Is your book an expression of free will, or just the universe having already set its predetermined course towards large colliders and beautiful theories, but at the same time emerging a Sabine to counter it?
Before I answer that question, I hope you allow me a little piece of advertisement. I have a video upcoming in my channel about the question of free will, which will be in Saturday in 3 weeks. So this weekend, I have a video on Oh, it's in my series on quantum mechanics, understanding quantum mechanics. And then the weekend after this, I have one on differential equations, which is building up to explaining the issue with free will. And I'll explain why I don't think free will makes any sense. And so to go back to this question, it's not that I'm a free will denier. I just think the idea of free will is incoherent, absolutely meaningless, and we would be better off not talking about it. So I think that's what the science tells us pretty clearly. And, you know, to this question, I constantly get this, like, you know, do I really think that my whole behavior was predetermined when the Big Bang happened? Yes, of course. I think a lot of people have, you know, give themselves a headache over what this means exactly. How do I make sense of this? Well, the thing is that arguably, as we, I think, have all experienced, free will is a very useful thought concept to work with. You know, we act as if we had free will, whether or not it's actually a real thing. And I've absolutely no problem with that. You know, if you're happy believing in free will, that's fine with me. You know, keep on doing it.
Yeah, I got your point, and it's nice that you made it clear also for review. By the way, about YouTube channel, because you mentioned it, you had a video last time, follow the science, nonsense, I say. You were very emotional on that video. I liked it. And it seems that, and by the way, you continue for the readers, for the Romanian listener, I say, you continue on the video. I say, science does not know the direction. So basically, you make a very nice point in the video that science is not the one to decide. Science gives you the options, but you decide, you know, coming back to the following question. But there is somebody else who saw the video, Catalina 76767. Okay. And Catalina wants to ask if, you know, okay, science tells you what it is, but it doesn't give it a direction. And she wants to know if science become like, there is a lot of policy involved in science. So it's like today in the world of science, is science getting too much policy instead of real science inside the science? If you understand my question. So it's like policy, I mean political things. Too many political things coming back into the science. And I think you referred in that video to, for example, global warming, where you basically said, look, be careful because science tells you things, but there are other people who take the things from the science and tells you something else. So did really science today become too much, you know, the attention of the political things and is misused by the political guys? That's more or less the question from Catalina.
I think this depends very, very strongly on the topic. It's certainly difficult for climate science and also for public health in general, but currently for epidemiology in particular, yeah. for reasons we're all familiar with. That's just, it has become very, very strongly politicized, and this, of course, influences the community, and I think it's not necessarily for the better. You know, I think to some extent scientists are kind of they're afraid to say certain things, and you know, I don't know to which extent this is true, but there are people who have argued that this is one of the reasons why climate scientists have on various occasions actually underestimated how quickly changes would kick in. And we see this now. If you look at the curves, you know, they seem to have been overly conservative in their risk assessment. And of course, you know, in hindsight, you never really know what happened, but it's quite possibly because they didn't want to sound alarmist, to use the catchphrase, right? And so that's certainly, it's a very difficult situation. And there are certainly things that we could do better, I think, where we're, you know, the whole world is still learning how to integrate scientific knowledge into politics.
Yes. So coming back to like last 3 questions, I start with my question and then I put the other 2, because I really admire you. You are like a wonder mom. You have 2 kids. You are a researcher in a field and you popularize a science. And I'm a YouTuber myself. I know YouTube takes time. It's easy to look at the YouTube and say, well, you just do it like that. It's not. It just takes time. And you also write books. Again, Romanian readers, Rătăciți, prin formule, Lost in Math, the book we are talking about.
Well,
how are you able to make it all?
I've written one book, so, you know, it's not books plural, it's overemphasizing writing output.
Writing the next one. But how do you manage it all?
Well, I guess it's the things that I don't do. I mean, so I don't watch TV, but for example, I pretty much don't watch any movies unless I'm on a plane and there's nothing else to do. Most of the books I read are popular science books, and I convert these into book reviews, or I use something for my YouTube channel. So I'm very much a recycle and reuse person. I try to be as efficient as possible. You know, you do what you can. It doesn't always work. You know, if you look at my YouTube channel, you will notice that sometimes there are just gaps. You know, I try to put one out a week, but sometimes it just doesn't work. And then that's the first thing that has to go if there's something research-wise, a deadline coming up, that kind of thing. Yeah, so I mean, maybe I should add there that part of the reason I'm doing this public outreach is that, as you said, I work at a research institute. I don't have teaching duties. So I always feel a little bit that I'm lacking this educational component. And so it's not technically part of my job to do that kind of thing. So I'm not getting paid for it. But in spirit, I regard it as part of my job as a scientist to tell the public what we're doing.
Yeah, I think you really do a great work for this public outreach, and it reaches young people. So I have a question from a young people who is actually scared a little bit. And I'm going to give you an example from your book where you discuss about LHC diphoton bomb, which was at the moment and then disappeared, where you say in the 8th month since its discovery, more than 500 papers were written about a statistical fluctuation. So these young people look in the field, they say, oh, do I want to be a theoretical physicist? So Damian wants to ask you, what are the fields of theoretical research you consider now advisable to start a career? It's like, would you advise him to do fundamental physics research still? Or you do advise him to move to a little bit other fields? Or what are the fields?
So maybe I should clarify, because that's a confusion which a lot of people seem to have. Theoretical physics does not only exist in the foundations of physics, but they're pretty much all disciplines, sub-disciplines in physics have a more experimental and a more theoretical part. It's not always as separated as you have it in particle physics, but there's certainly always people who specialize more on, you know, making the experiment, analyzing the data and so on. And then there are people who specialize more on explaining that data or making predictions. So, I mean, it's a pretty broad question. It depends a lot, of course, on what you're interested in. You know, I would never recommend to someone to go into a field they're just absolutely not interested in. What would be the point of doing that, right?
Yeah, I will make it more specific because I have a similar question from Cosmin. He says, I like theory of fundamental physics, but is there a future in this field? Would you advise me here to have a career, you know, in the research of theoretical fundamentals of physics? So
well, So if you just want to know personally my answer, I definitely do think that there is a future. As I indicated earlier, I think that if we solve these problems that we currently have, we're going to open a whole new, how do I put it, a new little doll inside the Russian doll, and it will, you know, it will teach us some new things, but it will also bring up new problems, and it will be very exciting. Of course, the question is like, how long will it take to get there? So I kind of hope that it will happen within my lifetime. So the people who are now, you know, in high school, maybe about to start studying physics, they may be in for a very, very exciting time. Yeah,
I have a kind of question from Robert, who wants to ask you, what actually did attracted you when you studied math and physics? Is there a moment in your lifetime when you were young which really marked your way, really pushed you in this direction, or something, a passion which you had when you were young? Is there a moment in life which was definitory for you, what you are going to become or what you are going to become?
Well, I guess I'm a very common example there. So my story has probably been told 1,000 times. I was always very interested in science fiction. I just thought this was, you know, this whole story with the warp drive and additional dimensions, faster than light travel, going back in time, you know, fancy weapons, that kind of stuff. I always thought this was absolutely fascinating. But there was always, you know, this nagging voice that says, but actually it doesn't really exist, right? So that's always, and so I became very interested in finding out, well, what is actually possible in reality? What can you do? Why haven't we already, you know, space travel to visit other planets? What's the problem? So this was the one aspect, and the other aspect was that I was always good at math.
Yeah, which helps in physics. Yeah, I always tell to the Romanian, you know, young people, you want to study physics, be sure that you know math. Don't dream otherwise. So the last question for you, it comes from Marian. What do you miss in Corona time? How is your research affected by Corona problems around the world?
Yes, I guess it's very similar here to the way that it has been going with a lot of other people. You know, as long as the schools are actually open now here. So the kids just started school like 10 days ago or something. So that's a big step back to normalcy. As long as the kids were at home, like basically 24 hours, and we had to make sure that they do their homework and everything, it takes up a lot of time that is missing on other things. So there are lots of work stuff that didn't get done, basically. That's the one issue. The other issue is, you know, they're just, online communication like we're now having has its limits. There's just, you know, it just doesn't work as well. It's much easier to have a misunderstanding that keeps on lingering. And even though, you know, we have all, I think, become familiar with screen sharing and look, here's this equation and there's that, I find it really hard, especially, you know, I work with a lot of people who are like me, not native English speakers. And if there's even a little bit of, you know, audio problems, like you have it so frequently, it's just really, really hard to understand what they're saying. And you end up in this loop where you're asking like 10 times, like, I didn't get this. Could you repeat this? Could you repeat this? And it's just so frustrating.
Yeah.
So yeah. I hope it will become better.
Yeah, we all hope. Sabine Hossenfelder, thank you very much. For the people who were watching on Facebook and didn't know what we are talking about, we were talking about a book which Sabine wrote 2 years ago, Lost in Math, and which was translated in Romania by Editura Humanitas, and it's called Rătăciți prin formule. So I would advise you to check the book, Rătăciți prin formule, and buy it. Hey Sabine, thank you very much. It was very nice to talk with you.